In this lecture, we will learn how to write, assemble, debug, and execute the assembly code. I am using the NetWide assembler. Linker is the A-link, and the debugger I am using is the Advanced Full Screen Debug, which is abbreviated as AFD. The statement to write the assembly code is: the problem states we have to calculate the sum of squares of 2 and 3. And there is a restriction that we cannot use the multiplication instruction, but we have to use only addition to take the squares of 2 and 3. And we know that we can take the square of a number by adding the number itself. So here is the code to solve the given problem. The file name is fir.asm and extension of the file should be asm. We can use the text file to write the assembly code. Just rename the extension to asm. First line of the code states that whenever our code would be loaded into the memory for execution, the starting address of our code should be 100. Similarly, to be executed on processor, the starting address of PC or IP should be 100 as well. First step is to move the value of 2 in a register, which is AX. One point to keep in mind is that assembly is not case sensitive. Either we write small letters AX or capital letter AX, both means the same. The next line of the assembly program states add AX to means AX equals to AX plus 2. 2 plus 2 AX would be incremented to 4, which is the square of 2. The next line of assembly program states move BX3, which means BX registers equals to 3. So BX register would get the value 3. Next line of assembly program is to increment the value of the BX register by 3 by adding 3, which means 3 plus 3 equals to 6. Similarly, the next line add BX3 again, adding 3 to the value which is in the BX. 6 plus 3 equals to 9, and this is the square of the 3. The last line of our assembly program is add AX BX. AX is on destination side and the BX register is on the source side of an assembly instruction. So this instruction means AX equals to AX plus BX. So the value of the AX register would get updated. AX now contains the value 4 and the BX has the value 9. We have to add both these values, 9 plus 4, and the AX register would get the latest edited value of 4 and 9, which is 13. The last two lines of our assembly code indicates the successful execution of our code, and now the CPU can get its resources back. We are moving 00 to AL and 4C to AH of the AX register. As we know, AX register is further divided into two 8-bit registers, AH and AL. And in the last line, generating an interrupt to the CPU to indicating similarly these two lines are acting as return 0 of the high level language, indicating CPU to successfully exit our program and release the resources. Here, the commands are given to execute the assembly code using NASM. CLS command can be used to clear the screen of DOS box. We have to mount towards the directory where we have placed the assembly code file, which was fir.asm in our case. Then to assemble the code, the command to be used is NASM, then the file name, which was first.asm, -o is the key to generate the object file of the assembly code, and then we have to give the name of the file in which our object code should be present, which is fir.com. If I execute this object file fir.com, then nothing would be printed on the screen as I have not written down any output command in the assembly code. But we can debug our code, which we would do in a little bit time. Here is the scenario of generating the object file in NASM and then executing the object file, but there is nothing printed in the output as I have mentioned earlier. The next step is to understand the object code. When we generate the object code of our assembly code, I would explain it with the help of a scenario. Let us suppose in assembly code we have an instruction add ax bx, and when we assemble this instruction, the corresponding machine code generated for this instruction is 01D8. Now from the machine code, how we would understand that where is the opcode and where is the operand? Opcode means the operation code, which operation to be performed in this instruction, and operands means on which this operation to be performed. From assembly instruction we can easily find that add is the opcode and ax, bx, which are the registers, are the operands. But from the corresponding machine code, it is not easy to understand. So we have the word representation, which is for two types of representations. One is Endian. Little Endian representation is also being used by Intel, which is the scenario in our case as well. In Little Endian representation, least significant word would appear on the right side and the most significant word would appear on the left side of the machine code when translating the assembly code to machine code. Most significant always indicate what is the opcode, and the least significant would always indicate what is the operand. So from 01D8, Little Endian representation means 01 is the opcode word and the D8 is the remaining word representation on the least significant word side, representing the operands, which are the registers AX, BX. Whereas in case of big endian representation, least significant word appear on the left side and the most significant word appear on the right side of the machine code. Again, machine code includes opcode and the operand, and most significant word is representing opcode again. So if the translation from assembly to machine code would be done using the big endian notation, then 01 would appear, which is the opcode on right side, and the D8, which is representing the operands, would appear on the left side in case of big endian. This is the difference between little endian and big endian notation. The scenario we are using is based on little endian notation, so the left side word representation would represent the opcode in the machine code, and the remaining word bytes would represent the operands. Intel is also using the little endian representation. The next step is to generate the list file and to print the list file content, where the list file would contain 3 further partitions. The right side is the assembly code, then there would be the machine code, and alongside of this machine code would be the addresses of each instruction in hexadecimal. Here we can see that the instruction add AX BX is being translated to 01 D8, which is the little endian notation. So 01 is the opcode, means add, and D8 is representing the registers AX BX. Now I would explain how the addresses being allocated to each instruction while translating the assembly code to machine code. In the following scenario, list file is being printed on the DOS box. The right side assembly is the assembly code. Then on left side, this assembly code is being translated into the machine code. Here the question arises in mind that the machine code should be in the form of zeros and ones. But we know that the hexadecimal representation is easily understandable, and one hexadigit represents the 4 binary digits. So it is compact form. Alongside of this machine code, here are the addresses of each instruction of our code. These addresses are again representing in hexadecimal. On line number 3, our first instruction of the assembly code is being displayed, which is also being translated into the machine code. We can see the address of the first instruction is 00000000 in hexadecimal. The address is 0 because our assembly code is not loaded into RAM or memory as yet to be executed. If it is loaded into RAM, then the addresses should start at address 100. So whenever our assembly code would be loaded into the RAM, all the addresses here would be displayed after addition to 100, as I have written down the origin to be the 100 in the RAM. Now we will see how the address is being placed here and how the address is being decided. One thing to keep in mind is that one hexa digit means 4 bits or the 4 binary digits. Similarly, 2 hexadigits corresponds 8 bits, which is the 1 byte. And the addresses of the memory here also computes in the form of bytes. The first instruction is placed on 0th byte. Now we will compute how many bytes should be reserved for this instruction by grouping hexadecimal digits into two. First group is B8, second is 02, and the third is 00. Here I am placing these boxes. First box is at 0th location, which is B8. Second is placed at first byte, which is 02, and the third box would be placed at second byte, which is 00. 012 has been reserved for our first instruction, which is being displayed at line number 3. So the next instruction would start at location of byte 3 in the memory. If the next instruction would start from 012, then it can override the previous instruction in the memory. Or if the next instruction would start after any byte other than 3, then there would be creating a place or a hole or empty space in the memory, which is also not right. So the next instruction would immediately start after the first instruction ends. Here on line number 4, we see the instruction starts at byte 3. Again, we would count the bytes being reserved for this instruction by counting the groups of 2 of hexadecimal digits, as one group would mean 1 byte. 05, 02, 00, 3 groups, and starting from third byte. Third byte is reserved for 05, fourth is reserved for 02, and fifth is reserved for 00. So next 3 bytes would reserved for line number 4's instruction. Next instruction would start from location or byte 6 in the memory. Again, we would compute the bytes reserved for this instruction by computing the groups of hexadecimals. BB0300, 3 groups, starting from 6th byte, 6, 7, 8. 6, 7, 8 reserved for line number 5's instruction. So next instruction, which is at line number 6, would display or would be placed at byte 9 in the memory. Again count hexadecimal groups for this instruction. One group is 81, other is C3, third is 03, and the fourth is 00. 4 groups. 9, 8, 9, 10, 11, and 12. These locations have been reserved for instruction of line number 6, 9, 10, 11, and 12. So the next instruction of line number 7 should start from location 13. But here it is written as D, as in hexadecimal 10 is represented as A, B is represented as 11, C is represented as 12, and D is represented as 13. E is represented as 14 and F is represented as 15. So here instead of writing down 13, it is written as D, which means 13 in decimal. D is in hexadecimal and 13 is in decimal. Here one thing should be kept in mind, that we have to count the bytes in decimal, but the addresses should be placed in hexadecimal. Count should be in decimal and the addresses should be placed in hexadecimal. Decimal is the base 10 and hexadecimal is the base 16. So for line number 7, we have to again count the groups of hexadecimal digits. 81, C3, 03, 00, 4 groups. Starting from 13, 14, 15, and 16. So line number 7's instruction would reserve up to the 16th byte. So the next instruction, which is displaying on line number 8, should be placed on 17th byte. 17 in decimal. We have to convert this 17 into hexadecimal, and we know that we can do it using the placeholder method. 16 ones are 16 and 1 would be the remainder. So 17 in decimal is displayed as 11 in hexadecimal. Again count here the hexadecimal groups 0, 1 and D8, and the counting should be in decimal, which means 17 and 18. Only 2 groups for line number 8. 17 and 18. So the next instruction should be at byte number 19. Again 19 is in decimal, so we have to convert it into hexadecimal by using the placeholder method. 16 ones are 16 and 3 is the remainder. So here the address is the 13 in hexadecimal and 19 in decimal. Counting again should be in decimal. 19, 20, 21. So the next instruction should be at 22nd byte in decimal, and to convert this 22nd into hexadecimal, again we have to take the LCM or the placeholder method should be used. 16 ones are 16 and 6 is the remainder. 16 in hexadecimal. Again count the bytes should be reserved for this instruction 1 and 2. So 22, 23 up to 23 bytes, 0 to 23 bytes has been reserved for our assembly code when loaded into memory, which means total 24 bytes in total, as the counting is being started from 0. So total 24 bytes has been reserved for our code in the memory. Next step is to debug this code. For this purpose, I am using AFD debugger, Advanced Full Screen Debugger, and the command to be used is afdfir.com, which AFD is the Advanced Full Screen Debugger, fir.com was the object file created. The code would appear in the debugger. The section I am highlighting is displaying the assembly code. On right top corner, microprocessor states can be indicated as it is displaying the values of the flag register, IP and PC, which is currently has the address 100 as our code is being starting at 100th location in the memory. The registers AX, BX, CX and DX. Initially AX, BX contains 0. We are using AX and BX in our code. CX is not being used by us, but it is containing 18 already and would remain the same as we are not updating the value of CX. To debug the code, or for step-by-step execution, we press either F1 or F2 key of the keyboard to execute step-by-step code. Here in this scenario, if I press F1, the IP would get updated from 100 to 103, which is the next location of the instruction in the memory, and AX would contain the value 2 in hexadecimal as we are moving the value 2 into AX in the first instruction. This is the scenario after pressing F1 or F2. As I indicated earlier, IP would be incremented pointing towards the next instruction in the memory to be loaded in the IR register to be executed by the processor. Value of AX would get updated to 2. Now after execution of 103 instruction, which is add AX2, AX would be updated to 2 plus 2 4, and the IP would be updated towards the next instruction's address, which is 106. As indicated earlier, IP is pointing towards 106, AX value is been updated to 4, and now the next instruction, which is at location 106, would be executed, which is move bx3. So after pressing F1, the bx values would be 3, IP would be pointing towards next location, which is 109. AX would remain same, which is 4. As indicated, IP is pointing towards 109, AX remains same, BX is now contains the value 3. Now, after the execution of the instruction at location or address 109, which is add bx3, bx would be updated to 6 and IP would be pointing towards 10D. As indicated, IP is pointing towards 10D, which is the next instruction's location or address, and bx value is 6. Now again the instruction is add bx3, so the bx value would be updated to 9 and IP would be pointing towards the next location. As indicated, IP is pointing towards the next location, which is 0111, and the bx value is now 9. The instruction at 0111 is add ax bx, so now the value of AX BX would be added and stored in AX after the execution of this instruction. So AX would be updated to 13 and IP would be pointing towards the next location, which is 113. Similarly, as indicated, AX is containing 13, which is D in hexadecimal, and IP is pointing towards the next location, which is 113. And we are moving 4C00 in AX to indicate the successful execution and resetting the value of AX to 0 in AL and 4C in AH. And then the next step would be to generate interrupt to CPU to successfully terminate this program, as we have done with the execution, and the resources can be released. So this was all about the debugging or the step-by-step execution of the assembly code. Now I would show you how to debug or step-by-step execute the assembly code in NASM using DOSBox. CLS is the command to clear the DOSBox. Now I am pointing towards the location of the assembly code by using the mount command. Now using AFD advanced full screen debug to debug the code file already object file already created, which is fir.com. Here you can see the debugger has been opened. Similarly, as I've shown you earlier, here the code is loaded in the code segment starting at address 100. IP is pointing towards the address of the first location, and AX/BX contains value 00, and we are using only AX and BX in our code. Here if I press F1, IP would be changing towards 103 and AX would contain the value 2. As indicated, IP is now pointing towards the next location or towards the location of the next instruction in the memory to be executed, and AX register contains the value 2. Now if I again press F1 to step-by-step execute, or I can press the F2 as well. The instruction here to be executed is add AX2, which means the value of AX would be incremented to 4 and IP would be pointing towards the address of the next instruction in the memory, which is 106. As highlighted, IP is pointing towards 106th location in the memory and AX contains the value 4. The instruction states move bx3, which means after the execution of this instruction, IP would be pointing towards the next instruction and the address the IP contains would be 109. Bx value would be updated to 3. As indicated. Now at location 109, we have an instruction add bx3. So the value of bx would be updated to 6 and IP would be pointing towards next location, which is 10D. In this instruction to be executed, add bx3, bx would be updated to 9 and IP would be pointing towards the next location, which is 111. As indicated. Now the instruction to be executed is add ax bx. So the value of ax bx would be added, 9 plus 4, and the updated value, which is 13, would be placed in ax, and 13 is represented as D in hexadecimal. So ax would contain D and IP would be pointing towards the next location, which is 113 as indicated. Now resetting AX to 4C00 and generating interrupt. That was all. Thank you very much.